Hello, everyone, and welcome to the Adafruit Show and Tell. I'm Liz. I'll be your host this evening. We're going to kick things off with some folks from Adafruit and then people in the community. And if you are in the community and you would like to join the stream, you can do that from our Discord. That's adafruit.it/Discord. Link to the StreamYard is in the live broadcast channel. But like I said, we're going to start with some Adafruit folks first. So let's hear from JP.
Hey, Liz.
Hey, how's it going?
Good. I'm enjoying trying to figure out what little decorations you have there. Some cool autumnal things. It's fun to spy on your decorations. I've been working on a cool synth.io project. I think it's cool, at least, which is diving into a little bit of the depths of how synthesizers work in general and how synth.io works in specific. Which has to do with waveform shapes. And so there are, we're familiar with things like sine waves and square waves, triangle waves and saw waves. And often in synthesizers, you can pick from a couple of those oscillators and maybe sometimes mix between them. And that tends to be how analog synths worked, because it kind of makes sense to be able to generate things like a triangle wave and then kind of filter it into a sine. But with digital stuff like synth.io there is sort of no limit. And so the shape of one cycle of a waveform can kind of be anything you want with many, many, many points. And you can noodle around with them until you get kind of the sounds you want. And what this tends to do is mostly adjust the harmonics. So you can like highlight little pinging frequencies above the main frequency. So in synth.io, there are tables that you can make. You can use equations, algorithms to generate, but you can also just kind of make these tables of numbers that are the values of plotting this kind of XY graph of your waveform. Yeah. So if you pop my camera on, you'll see I have a little prototype of just a 4-point waveform using these 4 little sliders here. Nice. This is a prototype using our Neo sliders that we have here, but I'm working on something that won't use those that I'll talk about in a second. So what these are doing is they're just saying what are 4 vertices or 4 points that make up this one cycle of a waveform, which can then be played at different pitches. So let me stop talking and just demo some sound. Cool. So what you're going to be listening for is just the changing character or tone of it as the harmonics change.
Yeah.
So you can see here, this one is kind of like a very sharp little sawtooth or a triangle. And so it's got these kind of high-pitched, buzzy sounds that are part of its character. If I just do a straight square wave, kind of loses some of that extra harmonics. And if I try to calm it into sort of a triangle shape, you can also quiet it just by kind of shrinking its amplitude down.
Yeah.
So now the waveform is sort of centered around 0. So these go negative 30,000 to positive 30,000 each.
Very cool.
So that's my prototype for this, and I'll be showing I have kind of a cool graphical demo that'll, I think, help explain this. I'm going to show on the show tomorrow.
Nice.
Using a software synthesizer. But the goal is to make a 16 fader version of this. So I'm going to be taking 16 of our 75 millimeter slide pots. They have a 60 millimeter throw. I'm building a PCB for it, and we're going to be able to do some really cool things even beyond this project with it. I think it'll be kind of a neat platform. We have a couple of 8-bit DACs or ADCs rather that'll work well to allow us to read these faders and do cool stuff with them. So that's what I'm working on.
Excellent.
Come on by to my show tomorrow, and we'll dive in even deeper.
That's going to be great. And related to that, I've been working on the product guide for that ADC, and I have a Circuit Python library that I'm working with Scott for writing. And having used it, like, it's very responsive with pots. It's very satisfying. So
yeah, I got an early look at it. At your I was able to use your example that you sent me. Thank you, and it's really nice. And these are, I think, just giving me 0 to 1023.
Yes. Yeah.
On these Neo sliders, because they're using a little seesaw chip, and I think that's the most they'll send. So we're going to get 0 to 65,000 basically with the. So we'll have much finer grain control, and with those extra points along the wave, you'll be able to craft some really interesting, I think, rich sounding synthesis.
Yes, it'll be hours and hours of synthesis.
Yeah, I just let it play ARPs and I goof around with it and zone out. It's loads of fun.
Yes. Awesome. Well, thanks so much, JP, and look forward to seeing your show tomorrow.
Sure thing. Thanks, Liz.
Okay, no problem. All right, next we're going to hear from Melissa. Hey,
Hello.
Melissa, how's it going?
It's going good.
Good.
So do you want to share my screen and
Yes.
other camera here?
Yes.
Okay, so I had showed off this paint demo a couple weeks ago, I think, or maybe last week, I can't remember.
Yeah.
And I have updated it now because I've written a new Qualia library, and that handles a lot of the initializing the display and everything.
Nice.
And even handles loading the touchscreen driver.
Oh, that's
so I just wanted to show, right now I have it loading with the bar graph, or the bar display here, and I just want to show how easy it is to switch displays. And so let me go ahead and power it off first. And then...
And so with this library, right now folks have to kind of have the init at the top of the code, but with this library, folks won't have to do it. It'll kind of be what they're used to with the other displays and display IO.
Correct. So
excellent.
I'm going to go and plug this in, and it'll initialize with the previous display, but in order to change it, we're just going to use this here and save that.
Oh, sure, we just got built.
My Echo device decided to try that. I had to unplug it.
They always hear you at the worst possible time, you know.
Yeah, okay, let me save it again here.
Okay.
Because I think it... Okay, so now it's just restarting with it. And now it just automatically sizes to here. Does a completely different touch driver. And then I'm going to go ahead and hook it up again.
That's great. And that touch demo you wrote is very responsive with that driver. I was playing with it today to do send a demo over to Pedro for a project I was working on, and it's really nice. So great job with that. All these displays.
Thanks. So I'm going to go ahead and show it around here. And then as soon as it comes online, I'll save that. And now rebooting. Okay, and here it's just loading, completely different touch driver than the previous one, and I didn't have to do anything other than tell which display.
That's awesome. That's great work. That's going to be really handy for folks.
Cool. Oh, one of my favorite parts about this is I have it so that it's going through on the library, and it just looks at all the displays that are added, and it kind of goes and automatically adds them into the displays class here. So just adding a new display is easy. It's not like keeping track of a separate list or anything.
Oh, that's awesome.
So it really like kind of puts the power of CircuitPython out there. It's really become so much more capable than when I started using it.
Yeah. Oh, that's great. Oh, thanks so much, Melissa. Looking forward to using it myself. I'm sure everyone in the community is going to find it really handy.
Okay.
All
cool.
Right. Thank you. Have a good night.
Thanks. You too.
All right. Now we're going to hear from some folks in the community. Let's kick things off with Bob. Hey,
hello, folks. I'm doing well. And yourself?
I'm good. Thanks.
All right. What I would like to show is a product that we've worked on for a couple of years. It's called PockletFrog. It's a USB piece of test equipment. It has a power supply, a fully programmable power supply,
cool,
a voltmeter, and a counter timer. And it's, I'm going to share my screen.
Okay.
And I still see my camera.
Should be, there's a present button kind of at the bottom.
Yeah, and I hit share screen. Sharing screen easiest with two monitors. Blah, blah. I click share. Oh, there's another window up here. There we go. I didn't finish the handover.
Awesome.
Okay.
There we go. Perfect.
So we've got a user interface window
Great.
that lets you find a frog. Gives you the serial number. You've got a voltmeter. You've got a counter timer, and all these measurements are made simultaneously and presented. And we have the power supply. So you can turn the power supply on. We have safety limits. You can just use a scroll wheel and just dial it up.
Cool. Nice.
It goes against your safety limit. It's a 20-volt power supply. It can run off just plain USB. It'll still give you 0 to 20 volts.
Okay.
You can use external power, and it'll give you up to 40 watts of power.
Nice.
And then the other thing it can do is it gives you programming without having to write Skippy code or Python or whatever your favorite thing is for delivering that. So, for example, if you can go back to my camera, can you do that, or do I have to do
yes.
that?
Yeah, I'll do that.
So, this is the external power jack, which gives you up to 40 watts. We're also introducing, I guess this is actually its debut, a series of education board and engineering helper boards that just plug in the front of the PockletFrog.
Oh, cool.
And just set to your bench now. This is an education board for high school, tech schools, first year in college.
Nice.
On resistor theory, resistor sensors. So if, for example, we are in the thermistor lab and we turn it on to 5 volts, we have a, pull it over here, we have a spreadsheet that comes with the product.
Okay.
And it gives you a mess of templates for just like what JP was talking about, simple sine waves you can have your power supply deliver.
Yeah.
If you really need a tangent wave, there you go.
Nice.
Square waves, pulse, triangle waves, and all the way down here, that's power supply stuff. But you can also say, I want my voltmeter not to read volts, but temperature. So if you look here, from the template, here you put in your coefficients for your thermistor, and your voltmeter is now reading temperature. And there's, see in the upper right corner, it's 74 degrees down here.
Sweet.
That's pretty close to accurate.
Yeah, that's awesome.
And for the waveform generation, if I hook up my little scope, which I can show on the camera. So we've got the power supply turned on. We can go to calculations. One of the waveforms here is a standard automotive test waveform.
Okay.
This is a cold crank. So if you're starting your car up in the winter, this is a worst case waveform. This is kind of a complicated example, but we can tell it to execute it. And if you look at the scope screen, we're up at 12 volts. There's the first dump.
Oh, yeah.
And we're playing back a cold crank waveform.
Very cool.
So it's kind of an instrument in a class by itself. There isn't a lot of stuff out there. It gets around a lot of the hump of programming to generate repeated test waveforms, repeat a battery discharge over and over all night to make sure that your embedded software behaves correctly, saves the non-volatile parameters or whatever you need.
Very cool.
It does a lot for a design and test.
Yeah.
And we have a bunch of material on the website you can download. I don't know, are you looking at my screen now?
Yeah, we see your screen. Yeah.
And Standard Measurement US has set up a little shop. So we're available on our site.
Very cool. Well, thanks so much for coming by and showing us this walkthrough. It's very cool.
Thank you.
Thank you. All right. Have a good night.
You too.
All right, now we're going to hear from Bradán. Looks like he's going to play us out. Hello.
Hey, how's it going? Hey,
Good,
by
how
the
are
way,
you?
I've always wanted to say I love your microphone. I just think that's so cool.
Oh, it's actually a little 3D printed like pop filter thing. So thank you.
Yeah, very cool. Actually, I dovetail into actually what we started with, which was this notion of synthesizers. And so I planned to go to SuperCon, didn't get there, but they had this idea of a waveform generator mixed with a vector scope. And I said, well, that sounds really kind of cool. And so they were using a Raspberry Pi Pico. And I did some research and did some digging around, and I found some bits and pieces, and I was able to glue it all together for taking a Raspberry Pi Pico and something that's referred to as an R2R, which basically says it's a resistor and it's 2x of a resistor. And you can create a DAC, a digital to analog converter, just out of resistors. And so this is a quick picture. I actually created two. Oh, I got to change my screen real quick. I actually created two 8-bit DACs. There you go.
Sweet.
On the Pico. So it literally is just a Pico and 46 resistors.
Wow.
Yeah, I know. It's kind of and it doesn't look very pretty. I soldered them directly onto the GPIO pads. But it does work. So what you now see over here is just some rotary encoders that I've got that have set up. And you can see I've got channel 1 and channel 2. It actually has 2 full channels. So let me just quickly set, this is set up, as you can see on channel 0. I've got a sine wave set at 1000 hertz or kilohertz. So let's just turn that on real quick. And you should see when I change one of my screens, there we go. The yellow line there is that sine wave.
Okay, yeah.
And on channel 1, I could create the same one if I wanted to. I could set it to be a sine wave, and if I turn it on, you'll see the purple line becomes the same as that one. It's just out of phase, and I can adjust the phase and do fun things like that.
Oh, cool.
But you can also mix. So, for instance, right now I have a sine wave, but I could say that I want to use frequency modulation and add another sine wave to it. And I want the relationship between the two to be, let's make it 5 to 1. And now when I restart that one, that's what I end up with for a waveform. So that's a sine wave mixed with a sine wave. One is 5 times the frequency of the second. And I've got access to, so let me just quickly change. Let's say we're going to set this to be 10 times, but instead of mixing it with a sine wave, let's mix it with a triangle wave. And this should look pretty familiar at this point, because what's going to happen now is the sine wave is going to be mixed into a triangle wave.
Oh, cool.
Now, if I set the yellow one as my reference to also be a triangle wave, you'll actually be able to see, there we go. And see, I can actually fit one inside the other.
Very cool.
Yep. And so this is nothing more than a Raspberry Pi Pico and a bunch of MicroPython code. The trick is it uses the DMA. It uses 2 DMA channels linked together. It uses a state machine and it uses PIO. But it's all written in MicroPython. It's all open source. I've published everything out. I use GitHub instead of GitLab, but it's simply called AWG, the number 2, CHAN for arbitrary waveform generator 2-channel. And it's been a fun thing to play with. It's kind of interesting. Like I said, I hadn't done a lot with MicroPython, and I hadn't done anything with the DMA channels or the PIO.
Yeah.
And on the Pico, those are just incredibly powerful. They're just a lot of fun to play with when you kind of get understanding of how they all work together.
That's amazing. And I've seen this project kind of floating around, so it was great to get a live demo. And I agree, like the RP2040, it seems to just have all this capability that
I never cease to find something crazy to do with it next.
Yeah. Well, definitely drop a link to your GitHub in live broadcast chat so folks can check it out.
I will do that.
Excellent. Thanks so much for coming by.
Thanks. Have a good day.
Have a good night. All right, that's going to do it for tonight's show and tell, but don't go away. In 10 minutes, live is going to be Ask an Engineer with Lady Ada and Mr. Lady Ada. Until next time, have a good night. Bye, folks.